Okay, so what we learned last time is the comparison between electrostatics and magnetostatics, right? So if you have an electrostatics, there are two governing equations. One is about the divergence of E, and the other is about the curl of E. And electrostatics, curl of E is 0, whereas divergence of E is a charge density, right? So as I said earlier, electric field is created in a diverging way from a charge, right? And on the other hand, for the magnetic field, divergence of B is 0, and curl of B is the current density. So unlike electric field, magnetic field doesn't have any point source, but it's created in a rotating manner from around a current, right? So that's the big distinction between these two. So the curl of E is 0, divergence of B is 0, okay? And that distinction makes a difference in defining potentials in both cases. So in electrostatics, because curl of E is 0, electric field can be written as a gradient of a scalar function, right? And that made our life a lot easier because we can deal with scalar potential rather than complex vector quantity. And then we got the solutions for point, line, surface, volume charges. And then similarly, magnetostatics, divergence of B is 0, right? And then that gives us, that allows us to express B as a curl of a vector potential. And then this looks less useful because anyway, vector is representing another vector, right? It's not like a super useful thing. But the thing is, we have a gauge freedom, which means we can choose divergence of A in whatever manner we want, okay? So in this case, we choose divergence of A to be 0. Then the equation for the vector potential A is exactly same as Laplace equation, right? So because mathematical form of these two equations are exactly same, the solutions are also exactly same. So for line charge, surface charge, and volume charge, your vector potential can be written readily like this, right? And then from this, the line charge equation, we can rederive Biot-Savart's law. So just by taking curl of it. So by taking curl of A, we were able to obtain Biot-Savart's law, right? And then what we talked was about the magnetic dipoles. Okay, so we have a current carrying loop, and then we want to know the magnetic field pattern very far away from the loop. Okay, so in this case, we can make a expansion like Fourier expansion. Sorry, not Taylor expansion. So by using the fact that R is much larger than R prime. Okay, and if we do that and doing some mathematical stuff, we get to the conclusion that A of this a small loop can be written as a mu0 m cross AR. AR is the AR vector divided by 4 pi r squared. And then m here is magnetic dipole moment. Magnetic dipole moment is current multiplied by vector surface of the loop. And then again, when you decide the direction of the surface, you should follow the right-hand rule, right? So if your other four fingers are aligned to the current direction, then your thumb is pointing the direction of the surface. Okay. So now you have a magnetic dipole. So you have magnetic dipole moment and a vector A, vector potential A. By taking curl of it, you can get the B field, right? And then if you take the curl of it, you get the B field, which looks like this: mu0, 4 pi, 1 over r cubed, and then 3, m dot AR direction minus m. So this equation should look very familiar to you, because this one is what you already saw in electric dipole, electrostatics and electric dipole. Okay, so as you know, as you probably even done some experiments, your magnetic dipole, like the magnetic field due to a magnetic dipole, looks like this. This is a very famous field pattern. And then you probably learned about like this many times when you were young, right? This is a magnetic dipole field pattern. Okay, so now you have a magnetic dipole. You can simplify many quantities using this, this magnetic dipole. So here's one example. This example asks you to find the force and torque applied on this rectangular current loop. And here the current is rotating like this. Okay, and then B field is along y direction. And the magnetic force only occurs when the direction of the B field is perpendicular, or like at least not parallel to the current. So these two line segment, CD and AB, doesn't do anything in terms of force, right? And only this AD and BC plays a role. So how to obtain the force amount? Well, that's just I L cross B, right? And you know L in this case, and then B is given. So depending on the angle alpha that this circuit is making with respect to the direction of the magnetic field, you can obtain the force. The thing is, if you actually calculate the force on this line segment is going up, and then force on this line segment is going down, and the amount is exactly the same. So in terms of net force, it's 0, right? So this force and that force cancels each other out. So there's no force, right? But in terms of a torque, of course, it's non-zero. And then you can obtain the torque by adding up R cross F, right? This is the definition of torque. And then the torque becomes non-zero, and then this guy, this rectangular loop wants to rotate like this, right? Because the force is applying on upper direction here and lower direction there, so it's like it wants to like rotate like this. So torque is non-zero. And in this case, if you evaluate the torque, it's actually same as M cross B. Okay, so if you calculate torque from the fundamental definitions, and then you will realize that torque is equal to M, which is the magnetic dipole moment of this loop, which is I multiplied by surface area, which is LW, and then the direction of the loop, say AN in this case, right? And then multiplied by B. So that's exactly the same as torque. So if you define the magnetic dipole moment, you can derive like useful quantities in a very simple manner. So that's the beauty of defining dipole moments. And finally, here I compare again the electric case and magnetic case. And first, dipoles. As I said, as we discussed earlier, in case of magnetic dipole, vector potential can be defined like this. And then if you take curl of it, you get the B field, which looks like this. And then we already discussed electric dipole. Electric dipole, you have a scalar potential like this, and then taking negative gradient of it, you get the electric field. And then as you can see here, this equation and that equation looks exactly same, right? It's exactly same. So you can see if you have an electric dipole here, you can expect this type of dipole field. And then here too, if you have a magnetic dipole, which is actually a current carrying loop, your magnetic field shows exactly same pattern. Okay, same dipole pair. And now going back to electric monopole, again, if you have a charge, this charge creates electric field in a diverging manner. This is monopole, like just one charge, right? So note that dipole is actually net charge is 0. They're just separated. And here we have non-zero net charge, which is monopole. And here in the magnetic case, because divergence of B is always 0, there's no magnetic monopole. Okay, magnetic dipole, magnetic field never being created in diverging manner. Okay, so it's like there's nothing like a magnetic monopole in this case. But dipole, both case exist and they have exactly same field pattern. Okay, so is there any question before we move on to the next lecture notes? Okay, if not, I'll move on to the next lecture note.